Let's draw just a little sketch of the neuron. So here's our tree-like structure with our dendrites. That's all connected to the cell body, and then that has our axon, and then this ends in our axon terminals, and then there's going to be another over here. So there'll be another neuron with the dendrites connected. There's our cell body, and then another like that. So that would be 2 neurons, for example. That's Chad's drawing. Electricity doesn't move in a neuron in the same way as we've been talking about, in the same way as in a wire. Oops, in a wire, where we think of electrons sort of moving in this direction. It's not really the same as that. Instead, ions move across the cell membrane. Perpendicular to the axon. So we have potassium ions. They'll move in or out of the cell membrane. This would be the cell membrane right here. That will cause the potential inside the neuron to be either positive or negative. And then the motion of these ions moving perpendicular to the neuron causes the potential to change in the axon. And then this affects the ions further down. Further down the axon. The electrical signal then moves down the axon like a wave or like a pulse on a string or rope. Like if you're doing the thing in the gym with the ropes and you have this pulse that moves up and down, you know, the rope isn't actually traveling up and down. It's just you have this energy wave that goes through, and that's sort of like what's happening is that I have this wave of potential that propagates down the axon. Not that charges are moving along the axis of the axon. Instead, I have charges moving in and out of the axon. And that's causing this change in potential that propagates down the entire length of the axon. So we still get the same effect, that we get the effect of an electrical signal traveling across a distance, but it's not happening in the same way as when we think about it in a wire. I have a video I'll show you in just a bit. It's really kind of cool, actually. Now, the membrane potential, this gets a little weedy, so bear with me. So the axon has potassium, A+, and then anions. I'm going to call that A-. So this is a potassium cation. Remember, cation is positive. And the A- is just a generic anion. It's made up of different molecules. So the axon has these potassium cations and these anions on the inside of it. And these are separated by the cell membrane. From the sodium ions, cations, and chlorine anions on the outside of the axon. All right, so if this is my cell body, there's my axon, there's my dendrites. I have these potassium and organic anions, and then out here I have sodium and chlorine anions. I have the potassium and the anions on the inside of the cell, and I have sodium and chlorine on the outside of the cell. Now, there are more potassium inside than out, and sodium outside than in. There's more sodium ions outside than in. So I have a greater number of potassium on the inside, a greater number of sodium on the outside. So by diffusion, that is that ions will tend to move from higher to lower concentration. So because I got lots of potassium on the inside, it's going to tend to move out by diffusion. So the sodium ions move inside the axon because I got lots of sodium out here, so they tend to move in by diffusion, and the potassium ions will tend to move outside the axon. And this is called a concentration gradient. Because I have a higher concentration of one ion on one side, they will tend to equilibrate, and so those ions will move from an area of high concentration to low concentration. So that's the first thing, concentration gradient. And then also, because of differing permeability, in the cell membrane for both the potassium and the sodium cations, more potassium ions move out than sodium ions move in. So I got all these potassium ions moving out, and then I don't have as many of the sodium ions moving in. Okay, sorry about that, I had a telephone call. So I have more potassium ions moving out than I have sodium ions moving in. So that means that the inside of the axon is going to become more negatively charged. And it's going to have a lower potential than there is on the outside. So there is a potential difference between the inside and the outside. So if I look at the, here's the cell body, there's the, I have a negative potential out here because I have negative charges. I have an overall negative charge, and I have a positive charge on the outside, a net positive charge because of this shifting between the different ions, and then so I'm going to have a positive potential on the outside. Negative charge, negative potential. Positive charge, positive potential. So in summary, the potassium and the sodium ions move by 3 different mechanisms, and these are important. You need to know these. First is just the chemical gradient. That moves potassium ions out and sodium ions in. The second is the electrical gradient. That moves potassium ions in and sodium ions out. And then finally, there's the sodium-potassium pump. And your book talks about this. And I'll show you a video that talks about this sodium-potassium pump. If you take probably physiology, I guess, you'll talk about this more. But the sodium-potassium pump moves potassium in to the cell and sodium out. So the potential of the shifting of these ions is really important because it means that the inside of the cell is slightly negative, and that gives it a resting potential. That's a term that you need to know, a resting potential of about negative 70 millivolts. That's the resting potential. We have a great video here. I'll link this on the website, and we'll pick up with this in a bit.